we can approximate the area under a curve in a finite interval using Riemann sums. So with the left Riemann sum, the left of each rectangle touches the curve, and we use the value of the function at these points to obtain the area of each rectangle, and then sum up the areas of each rectangle to obtain the approximation to the area under the curve. Now with the right Riemann sum, the right of each rectangle touches the curve, and similar to the left Riemann sum, we use these values to obtain the area of each rectangle and then sum up those areas. And the midpoint Riemann sum uses the value of the function at the midpoint of each rectangle to obtain the area under the curve. And we can observe that depending on how the function behaves, you may get an underestimate or overestimate to the approximation of the area under the curve. And you may also be given problems in a graphical, numerical, analytical, and verbal form to obtain an approximation to the area under the curve. And we'll develop equations for each of these separate methods and apply them in practice problems. The left Riemann sum can be used to approximate areas under curves, and the left of each rectangle touches the curve. So these values are denoted yi, and in the case where we use rectangles of uniform width, the approximate area is equal to the width of each rectangle, so that would be b minus a on the number of rectangles, and we multiply the width by the height of each rectangle and sum them together. So that will be the sum from y0 to yn minus 1. Because the initial rectangle has a height of y0 and the final rectangle has a height of yn minus 1, as defined by the function of the curve. Now where we choose to approximate the curve using rectangles of non-uniform width, then we basically have a separate width for each y value. So that will be delta xi, which changes for each rectangle. The right Riemann sum approximates the area under a curve over a finite interval using rectangles where the right of each rectangle touches the curve. So if we use rectangles of uniform width, then the width of each rectangle is b minus a on a number of rectangles. And we multiply this by the y values that touch the curve. So effectively we're summing up the area of each rectangle. So here we start with y1, and we end with yn. So as we can see, this here is the initial value, and this here is the final value where the rectangle touches the curve. And similar to the left Riemann sum, we can use non-uniform partitions and multiply each individual y value by a different width to approximate the area under a curve in a finite interval using the midpoint Riemann sum. We use rectangles where the midpoint of each rectangle touches the curve. So approximating the area using uniform partitions, the width of each rectangle is b minus a on n. Then multiplying this by the y value at the midpoint of each rectangle, we have y at 1/2, and then plus y at 3/2, and so on up to y, and the index of this final y value will be y of n minus 1 plus n on 2. So that gives 2n minus 1 on 2. And where we use non-uniform partitions, we can multiply each separate y value by a different width for each rectangle. And we'll see that in example problems. We can also approximate areas under curves over a finite interval using the trapezoidal sum, which can provide a much better approximation. So if we use uniform partitions, we can approximate the area as b minus a on a number of trapezoids. And then if we multiply the width of a trapezium by the average of the heights, so that gives the area of one trapezium, and then we do the same to obtain the remaining areas of the trapezia. So as we can see, only the first and final term are divided by 2, because the middle terms all sum together to cancel out the 2. So we obtain the following approximation to the area. And again, if you had different widths for each trapezia, then you calculate the area of each trapezium using those different widths, and then sum those together to obtain the area under the curve. Let's approximate the area under the curve using the left Riemann sum. So what we have here is 1, 2, 3, 4 and 5. So we're basically dividing this curve into rectangles, and when we take the left Riemann sum, the left of each rectangle touches the curve. So therefore, the area is approximately 5 minus 1 on 4 rectangles. So that's the width of each rectangle. And then we just multiply by the height of the left of each of those rectangles, which is given in a table. So that will be 11 plus 14 plus 19 plus 26. So that gives an area of approximately 70. Let's approximate the area under the curve using the right Riemann sum. So we divide this curve into rectangles. And now because we're using the right Riemann sum, then the right of these rectangles touches the curve. So therefore the area is approximately equal to the width of one rectangle. So that would be 5 minus 1 on a number of rectangles. And that's multiplied by the height of the right of each rectangle that's touching the curve. So that would be 14 plus 19 plus 26 plus 35 as given in a table. So the area is approximately equal to 94. Let's approximate the area under this curve defined by this function over the closed interval from 1 to 5 using the midpoint Riemann sum and 4 uniform rectangles. So basically, when we divide this curve into 4 uniform rectangles, and we're taking the midpoint of each of those rectangles to define the height of each rectangle. So this would look something like this. So therefore the area under the curve is approximately equal to 5 minus 1 on a number of rectangles, which gives you the width of each rectangle. And then we multiply by the sum of the heights of those rectangles, as defined by the midpoint. So over here we have 1.5, so that'll be the function f of 3 on 2. Here is 2.5 plus f of 3.5 to get that midpoint. And then plus a function of 4.5 to get that next midpoint. And then evaluate this and post your answer in the comments. Approximate the area under the curve using the trapezoid method. So we have the width of each trapezium as 1, so this is from 1 to 2, then from 2 to 4, and then from 4 to 4.5, and then 4.5 to 5, as given in the table. So these trapezia are going to look something like this, and therefore the approximate area under the curve is the sum of the area of each of those trapezia. So the area of the first trapezium is 11 plus 14 on 2, multiplied by the width of that trapezium, which is 1. And then for the next trapezium, we have 14 plus 26 on 2 by the width of that trapezium, and so on and so forth using the values in that table. So have a go at doing that and post your answer in the comments. Let's approximate the area under the curve given by this function over the closed interval from 2 to 5 using a graphical calculator, and we'll compare the result with that of the midpoint Riemann sum using 3 uniform rectangles. So if we enter the function for our curve and graph it, and then we could do a second function, calculate, and select 7 for the integral. And our lower limit would be 2, and upper limit in the interval would be 5. So that gives us an area under the curve of 69, which is going to be very close to the exact result because the calculator uses a much better approximation. Now if we use the midpoint Riemann sum to approximate the area from 2 to 5, then the area is approximately 5 minus 2 on the number of rectangles, which gives the width of each rectangle. And then what you do is multiply this by the function evaluated at the midpoint of each rectangle. So that will be y of 2.5 or y of 5 on 2. And then y at 3.5 and y at 4.5. And if you plug these values into this equation, and we get 3 on 3 equals 1, so you get the following expression. And then calculating that out, you get the following result, which is very close to the result we got using the calculator.